If you're here, if you're not here, it's nice to go back and just rewatch a lecture. Man, I wish some of my teachers would have done that. We didn't have the YouTubes back in my day, though. All right. The YouTubes on the internet. Now, not everybody did this problem correctly, but I want to see if you guys, I'm going to build off of this problem for what we're about to get into. Stay with me. What we're about to get into isn't anything entirely new on its own, but it's reorganizing stuff we've done and then interpreting what that means. So we're getting into the part where we're finally going to be able to calculate for ourselves. When I see a poll that was done, and they say 40% want to vote for this guy, 42% want to vote for that person, and at the bottom it says plus or minus 4%. So the 42% person is not going to win for sure because it's give or take 4%. It could be totally the other way. So where does that plus or minus 4% come from? Where we're going to learn, we're going to be able to actually calculate that ourselves. Yay. So this problem I'm talking about is 5-2C. So let me build one like 5-2C on the test. There were a few different ways you could answer 5-2C, but the main way was to look at what's the max and min usual values. So let's say, so everybody had a mean around 14, right? For problem number 5? And their standard deviation was around 0.3. So let's just say that. So this is like everybody's, but like nobody's. And then in part 2, I said we took a sample of, everybody had 5 or 6, so let's say 7. 7 years. And so the whole part 2 talks about the sample means. It talks about that sample kind of thing that I took. So I have to use the new standard deviation, like we were talking about earlier, right? So how do I figure out the new standard deviation from this? The one that works for groups of size 7. How do I figure that out?
0.3.
Yeah, the old one divided by the square root of n. So it'll be 0.3 divided by the square root of 7. So somebody help me out there. What do you guys get?
0.11.
Yeah, I like it. So I get like 0.113, right? 1134 is beautiful. 113 is the minimum acceptable. Got to go at least 3 places. I like it. Okay. So now, any question that's talking about a sample mean, asking questions about that, I have to use this. So, what would be the max and min usual values for this situation? Or even better, let me say this a different way. Let me relate this to what we're used to. No, I guess that's all right. Let's say it like this. Between what two temperatures lies 95% of the data. And this is actually very much related to that go up, down 2. But it's not going to be exactly 2 now. It's going to be a little more precise. How in the world do I get that? Holy shit. So this I give you is an area. We're going to go directly from an area. What can I figure out about these z-scores? Can I look up 0.95 in the chart, though? I can, but is it going to give me what I want?
Oh.
No. Because is 0.95 the area below one of the z-scores I want? No, it's between two. So for example, to get this z-score, what's the area below it? If there's 95% inside,
2.5.
there's 5% out here, there's 2.5 over there. I like it. Let me stop right there, you guys. Because it's symmetry, it's symmetric. So then, this would be 0.025. Can somebody help me out? 0.025 on the chart. What z-score does that lead to? Say again? Careful. This is not a z-score. This is an area. What z-score does it lead to? So you have to get as close as you can to 0.025. And it should be... Yes. Which if I rounded this would be what? 2. Negative 2, right? So what's this going to be? Positive 1.96. So isn't this up and down almost 2 steps? Which is where that general rule comes from. If I go up and down 2 steps, I catch at least 95% of the data. That's why we consider anything outside of there to be unusual. What's the probability something happens outside of here? 5% chance. That's pretty small. So that's why we define unusual that way. Okay, all right. So how do I make this into a temperature? Yeah. I got the z-scores. How do I make it into a temperature? What formula can I use that figures out x if I know z? Yeah, and in this case, because of where we are, I've got to use the new one, right? So the formula doesn't really change. I just have to use the right spread, the right number for the spread. And this is not individuals, this is a group of 7 years. So, all right. So now I can just do that for both of these. So can't you see, can I write this a little better then? Because they're both the same number, just different signs. Are you going, do you guys understand what, if I did this? Where z is 1.96, because the other one's going to be the negative of that. So I get 14, give or take, 1.96 times this guy. You write that up here. So now we got figure out this first. Figure out this piece first. 14, give or take what? It kind of makes sense. I want to figure out what I'm going to add and subtract from 14. Yeah, so twice this, it kind of makes sense. So 0.222, So it'll be like, so if I add it, I get 14.222. And if I subtract, I get 13.778. Say again? 221? So 95% of the of any groups of 7 that I pick are going to have an average between these two. That's the idea. All right. So that's very similar to what you could have done on 5-2C. You could have just went up 2 standard deviations, down 2 standard deviations, and said, oh, that 14.6, whatever it was, is outside of the usual. So it is evidence that something has changed. I didn't say what that thing was. That's for the scientists to figure out and the politicians to be confused about, but okay, so let me take this back down to let's kind of formalize a procedure for doing this. We got what they want from this? Okay.
What is that little sign at 613.7?
Oh, degrees Celsius. I just tried to stick a degree Celsius.
Okay.
Yeah. It's not some weird semicolon.
Yeah, I was thinking.
Yeah. It's like uber semicolon, no. So here's the idea. So far, we've done problem. Here's the broader idea. I wanted to do this example because this is something I could have asked on this test more directly. In fact, I did have a question before this that said, find the temperatures bounding the middle 89%. And you would have had to do all the work that we just did. So it is a problem that you should have been able to do at the time of this test. So it's old news. We're going to use that same process, though, to do something kind of new. If I take a sample of wild muskrat, what's a good wombats? There you go, wild wombats. Do you have any idea about anything about wombats? Does anyone know something about wombats? Do you guys know there are things called wombats?
Yeah.
Okay. So I don't know anything about them. I don't know how big they normally get. I have no idea, to be honest. I'm sure I've seen one before on TV. But what's that? I don't want to mess with them because they're kind of aggressive from what I remember. But let's say we take a sample of wombats and we get like an average length for them. Do we know the average length of all wombats? No. Is that something that somebody would want to know? Possibly. Not you, not your friend, but somebody somewhere in the world. Would they want to know the average length of a wombat? Yes. Or like something more close to home, the average length of a shark. Yeah, I'd like to know that, because if the average length is 2 feet, all right, it's not crazy. If the average length is 28 feet, I'm not going in there, right? You guys kind of understand there's a certain reason we want to know this. Is there any way I'm going to take every freaking wombat and get an average length of everybody, of all the wombats? There's no way in hell I'm going to do that, no. Right, put a little tag on them, and I'm just going to do that for the next 30 years of my life. I think I've got all the wombats. No, now there's a whole slew that's been born now. Oh, shit. No. So what we do is, if I take a sample, size n, right, and I calculate my x bar from that, I want to figure out, is there a way I can get a feel for what the actual population mean is? Now, it feels like there's no way in hell, but there is. Now, the full truth is that we normally don't know mu, right? That's what we're basically talking about, right? We normally don't know the population mean. And we also normally don't know the population standard deviation. But there are situations where we do know those. We do know the population standard deviation. So, for example, I know the population standard deviation of men's heights. So I could go in a certain city and take a sample of men there to see if their height is different from the average man in the United States. Are you guys with me? So then I could use the population standard deviation because I know it. Okay. For right now, assume sigma is known. The next thing we're going to do after this section is we're going to talk about percentages, but then we're going to talk about what do I do if I don't know sigma? What do I do then? And thankfully there is something we can do, and somehow it's related to Guinness, if you like Guinness. Doesn't mean I'm going to bring Guinness in, sorry. But it is related to Guinness somehow. Take a sample of size n. We get our x bar from that sample. We assume that we know this for the population. So we can use it because it's true for any, in this case, wombats. Right? So recall, we have this formula here And we just used it a minute ago to do that problem we did to figure out the max and min kind of usual, right? So let me kind of modify this based on what we're doing now. Do we know mu? No. But if I take a sample of size n, I can use my best guess. Anytime I take a sample, my best guess for mu is x bar. So we're going to use x bar. Okay? And let's say, so the idea now is, I'm going to, somewhere there's a real mean length of this wombat. I take a sample. Is it going to be the same as that real mean? More than likely not. In fact, I would put money on it not being that. Right? So it's going to be somehow different, above or below. Let's just say it's over here. So what I want to do now is I want to say, all right, if I want to be 95% confident that I catch the real mean. So I got my sample mean. If that's a well-chosen sample, the sample mean should be close to the real mean. Is that understood? Does that make sense? If I take any sample, a nice, good sample, what do I expect its average to be close to? The real average. If I took a sample of 80 Grossmont students and their average age was 72, I am suspicious about the random part of that statement. I mean, there ain't no way you picked 80 random Grossmont students and their average age was 72. Does that make sense? Good. So any sample I pick, if it's well chosen, random as much as I can, its mean should be close to the real mean. So the whole idea here is, if I go up and down so much, I'm going to figure out what that so much is. I can then be a certain amount confident that I actually catch the real mean with that interval. It's sort of like, I don't like fish. I don't like two fish. Probably because I don't like fish. But if I threw a fishing net out, how can I be certain I caught a certain kind of fish? Is if I throw a bigger freaking net out. Like that 18-mile long one that somebody had. I don't know if you guys heard about it. I'll stop. That's in the news. So how much do I go up and down? Well, here's the whole idea. So I don't know the actual mean. So I start at the sample mean. And I go up and down a certain amount. So if I want to be 95% confident that I catch the real mean, how far up and down will I go? 1.96. Isn't that what we just figured out a minute ago? I would go up and down 1.96 because that catches 95%. So it's going to be whatever the z-score is. If I want to be 90% confident, I would go out less. If I want to be 98% confident, I would go out a little more. So it kind of makes sense. If you want to be more confident, you better cover your ass better. You better go further out. Okay, I like it. And now can I use this? Can I use this? Where'd this come from? Where do I get a sample mean from? Probably from a sample, right? So if I take a sample and I'm talking about the sample mean, what do I better do with this? Change it. So this is the formula for what's called a confidence interval. It's going to make an interval from something to something, and I'm going to be such and so confident that that interval catches the real mean. Kind of makes sense, because any sample I take, its average should be close to the real average if it's a good random sample. So then if I go a little bit out from there, I should be pretty confident that it catches the real mean. Okay, I like it. Maybe. So let's see. Let's do an example. Say we know the standard deviation of grades on a standard test is 14.12. We take a sample of 38 tests. Find the 90% confidence interval for the... we take a sample of 38 tests and get x bar equal to 78. So we know what the population standard deviation is. This is kind of like, related to the idea of a SAT test. They know what the standard deviation is because they got all the frickin' data. If I go take a sample of these tests, a 38 sample, and I get an average of 78, that is not definitely the population average, but it should be close. So I want to find the 90% confidence interval for the true mean grade. And when I say true, I mean, for the population. Any sample mean I get is not the real population mean. Okay. So let's see how this works. You know me, I've got a handout that's got a lot of the steps kind of there. Here's the formula we're going to use. I'm going to write it again up here. Here's the beautiful thing about this problem is it's very much a plug and chug problem, but you got to know where stuff comes from. I've got to give you almost everything. The only thing I don't give you is the z. Somebody tell me, where does that z come from? Not out of my ass. Where does it come from? What part of that problem, what part of that setup tells me how to get the z? So remind me, if I have the sample mean here, and I want to be 80% confident, I got to go out this far. If I want to be 90% confident, I got to go out further. I got to catch more of the test grades to be 90% confident that I caught the real mean. If I want to be 80, I don't have to go out as far. So what controls how far out I go from the mean? Standard deviations. The z-score comes from how confident I want to be. That area that I want in the middle. So I've got a x bar, and I want to go up and down so far so as to catch 90% of the data. How do I know that these x bars are normally distributed? Because of course I have to know it's normal in order to get a z-score from an area. How do I know it's normal? Sample size is 38. That's greater than 30. Check. So can you guys, again, so how do I draw the picture for the middle 90%? Probably like this, yeah. Can you guys take a minute and try to figure out what those z-scores are? What's in the middle here? 90%. Because I want to start the sample mean and go out that far. So that's 0.9. Keep going. You got your z-score charts. So what area is out here then? If there's 90% inside, there's how much outside? 10% outside, so there must be 5%. So if you look up 0.05 in the body of the z-score chart, it should lead you to an asterisk. Say again? Kick ass. So this other one's going to be? Yeah. Funny thing is, I just care that z is 1.645. The plus or minus, do you guys see how the plus and minus is captured in the formula, right? Because I'm going to go up and down a certain amount of standard deviations. What controls how far I go is how confident I want to be. So if I want to be 80% confident, I'm going to go out far enough to catch 80% of the data. Then I'm 80% confident that I caught the right thing. I mean, that part hopefully makes good physical sense. So now do I have everything I need for this formula? What's x bar? The mean, not the definition, but what is it? 78. I love you guys. What's sigma? 14.12. What is n? 38. And now we know z is 1.645. So now we just plug all that stuff in. So here's the formula again. Start at the mean, you go up and down this many steps. Now it's really just, like I said, it's the idea is nice. It leads to this formula, and then it becomes like a plug and chug idea. So now I just got to plug stuff in. 78, give or take, 1.645 of these. 14.12 over the square root of 38. Got it. And me, I tell you, do this part first. Figure out this part first. This part, now let's see if this makes sense. I've said this a few times already. This is give or take. Plus or minus, give or take. When do you hear the phrase give or take? When I'm trying to estimate something, right? I'm going to be there in 2 hours, give or take, half an hour. Right? That's how much I think I'm going to be off by. That's what we call the error. This is the error term. So if I was like at a carnival and I said, all right, if you guess my weight to within 10 pounds, I'll give you a little fluffy animal thing, He's like, all right. So within 10, I'm letting you be off, up by 10, down by 10. That's the error that I'm allowing you to have. So that's why we call it the error. Kind of makes sense. So can anybody just plug this in an old calculator and get a number popping out?
3.768.
Let's see. Yeah, I like it. So we get 78 plus or minus 3.768. I like it. And then just do that. I love the people that ask me where the plus or minus key. 78 minus this up to 78 plus this, right? So it'll be 74.232 up to 81.768. If I did that right in my head. Now here's the part you're going to love, all right? As if you didn't love this enough already. But wait, there's more. So I really want this to make sense. X bar, anytime I take a sample, it's almost guaranteed that's not the actual population average, right? If I took 10 people in here and took the average height, I'm going to bet a lot of money it's not the same as the average height of everybody in here. You guys with me? Any sample, that's true for. So what I do is I go up and down from that best guess. This is what the book calls the point estimate. This is the best guess. Up and down from that best guess a certain amount based on how big my sample is and so forth. If I make my sample bigger and bigger and bigger, what happens to the error? What happens to this piece of n gets bigger and bigger and bigger? This piece gets smaller and smaller. I'm dividing by a bigger number. Doesn't that make sense? The larger my sample is, the more certain I am about what I find, I should need less to cover my ass. It just makes it smaller and smaller. I don't have to go out as far. That's beautiful. It makes total sense, hopefully. So here's the part you're really going to love. You have got to write a little sentence interpreting what the hell we just found. Right? Stopping here is not good enough. So here's how that goes. We are how confident? 90% confident. That the interval from what to what? The interval 74.232 what? That's just the grade, right? Not really anything. There's no units here. 74.232 to 81.768 contains the true mean grade. Which kind of communicates to us, would you say that's a very wide interval of grades?
No.
I like it. I got a yes and a no. Yeah, I don't know. It's like 7 grade points apart. I mean, you know. So, but if it was like 30 to 100, I'm like, that would be basically me saying I don't have a flipping clue, right? So the confidence interval kind of gives us a feel for how sure we are about what we found. So we got 78. We think it could be somewhere between there and 90% confidence. What chance is there then that it's not in here? 10% chance, right? And that's pretty good for me. 10% chance I'm wrong, it's pretty good. Okay, maybe. So let me do this. Let me see. Let me make sure you guys really get a piece of this. Does everybody got what they want from here? So again, visually the idea is that's my best guess for mu. So I'm going to build off of that using this idea that we've had forever. Ever since we did z-score, we basically, the next thing we did was this. But I don't have the mean, so I use x bar. How do I get x bar is by taking a sample, so then that's got to change. So to be honest, those are the same stupid equations. It's just I don't have the mu, so what's the next best thing? X bar. Oh, you got x bar? Shit, you took a sample, you better change that standard deviation. They're the same equation. And I go up and down just because I want to, if I want to be however confident I want to be, is related to how many z-scores, how many standard deviations I got to go out. So that's why 90% confidence is a 1.645 z-score. 95% confidence is 1.96. 80% confidence is 1.28. I don't have to go out as far to be only 80% confident. 100% confidence is infinity. So just like real life, can you ever be 100% confident in real life? No. Sorry. You can't. Oh, some of you guys are, yes I can. Well, pretend to yourself, but you can't. That's why I love stats. It's very honest. Okay, so let me do this. Sarah.
Oh, sorry.
All right, so the side that says section 8.1.